Can you guys hear me and
Yep.
see my screen?
Looks good. Sounds good.
Great. All right. Yeah. Okay. Yeah. Hey, everybody. I'm Mike McDonald, a storage engineer at Google, working on Parallel Store, which is our managed service offering of DAOS, as Jeff mentioned. Prior to this, I was working on the DAOS control plane team at Intel, so been around for a little while on DAOS. And today in this talk, we're going to take a look at performance comparison between the PyTorch suite running over Defuse versus a new native DFS interface added by our friends at Enacta. So I'm going to breeze through the background slides on PyTorch fairly quickly. I don't have a whole lot of time, and I just want to preface this by saying I'm not an expert on PyTorch. My intent with these, with the overview here, is to kind of provide some context and be generally accurate in the concepts. But if I get anything glaringly wrong, please point it out. Yeah, just for those who aren't familiar, lots of people, especially in this world, have probably heard of PyTorch, probably have a general idea of what it is. But from a high level, it's an open source machine learning framework. My understanding is that it's basically, there was an original Torch library, which is implemented in Lua, and this PyTorch provides a nice Pythonic interface to it. It's incredibly modular and customizable, it's fairly popular for that reason, or that and lots of other reasons. Yeah, so that's PyTorch as I understand it. Parallel Store, it's a little bit of marketing fluff here, but yeah, it's a fully managed HPC and AIML storage solution. It's based on DAOS, currently 2.6. The current offering provides throughput at 1 gigabyte per second per terabyte of data stored. You can take a look at the published performance document for more details on that. And it's available for use with the managed Kubernetes within Google Cloud, and also from standalone GCP VMs. So you can set it up, install the DAOS RPMs and client RPMs, and use it that way. Just to talk a little bit more about PyTorch. Again, this is high level, just to provide some context here. But you have the storage concept. You have a data set that wraps some kind of structured set of data that it has a specific number of elements and provides either indexed access or iterative access to the data. In PyTorch, the two paradigms are referred to as map style or iterable style data sets. So the image here is an attempt to show to help visualize a map style data set where the elements are accessed via index. So you call get item with an index number, and you get whatever it is. So yeah, this would be an example of a map style data set. And within PyTorch, as I mentioned, it's very customizable and extensible. So it's possible to add custom data sets or implement custom data sets to provide access to other storage schemes. The example here is you have a directory basically on disk, shared or otherwise. Moving up a level to a data loader, and it's responsible for managing higher level access to the data itself. So you get concurrent access from a distributed job, deals with MPI, and you get other fancy things implemented at that level, like doing batching and shuffling and torchy things, I guess would be the best way to put it. But yeah, so when you instantiate a data loader as part of your model, you provide the data set as an argument to the data loader, and it takes care of providing the data to the model through the data loader. So talking a bit more about the new DFS implementation. So as I mentioned, and Dennis mentioned earlier, Enacta Labs designed and implemented this custom data set and checkpoint implementations that wrap DFS in order to read and write from POSIX layout containers directly. So basically bypassing defuse for the IO side of things. It's has been mentioned. It's already in the tree. It's been in master for a few months now. I think it went into January, but yeah, so it's there. It will be available as a preview in the upcoming 2.8 community release, and it is already in parallel store builds. It's been in for the last month or two, so it's there to kick the tires. And just this slide for a little bit more context. I pulled this example from the README that Denis Baraknatov added to the DAOS source tree. The takeaway here is that using a DAOS data set is pretty similar to other data set types. Just has a couple of new parameters to specify the source DAOS pool and container, but then you basically just use it the way you would any other data set. So that should be familiar to folks who are already familiar with Torch. Okay, so with the context out of the way, we can talk a bit more about the benchmarking that I did for this. Talking about the servers, parallel stores and managed service. So the specifics are, are not really, they're kind of opaque. They're not really relevant to the end user. In this case, I did the testing with 100 terabyte parallel store instance. That's the largest we currently offer. That means that there are 25 servers with 1 engine per server. As part of the service, we also create the pool and container behind the scenes for the user. And when the user requests an instance, they can specify. We offer a few canned striping choices for the container to set basically the default directory class and object class. So in this case, it chose the minimum setting to optimize for better smallish file performance. On the clients, not a whole lot really exciting here to talk about. They're kind of middle of the road in terms of specs. The one thing I wanted to talk about a little bit here or call out was the importance of the event queue parameter. I wanted to make sure I was giving diffuse a fair shake in the comparison, and the first time I ran a benchmark, I started it at and went to bed basically. When I got up the next morning, it was still running. I was like, what the heck is going on here? And I had forgotten to set to change the EQ parameter. It defaults to 1, which results in abysmal performance. So just as an aside, I think we should probably set that default to something a little more aggressive or useful to give a better out of the box experience for people who are running diffuse. So I mean, sure, you can read the documentation and say, oh yeah, you need to set that to something else, but I think half of the thread count, the default thread count is 16. So, I mean, in this case, I wound up using 8, and that the performance was about as good as I could get. So I don't know, I would say 4 or 8, something like that. But yeah. Okay, so the benchmark itself, DLIO from our friends in the LCF at Argonne National Lab. Basically, the benchmark here is that it evaluates the performance of a deep learning storage solution without actually needing to run, GPU, run on GPUs. So it simulates the GPUs. And the parameters chosen here, I did some earlier benchmarking a couple of months ago, and I have some slides from that at larger scales. But those were kind of ad hoc. I was still trying to figure out how some of the stuff worked. And these parameters were chosen to more closely match what I've found in other benchmarking efforts, I guess is the best way to put that. So this is it's a bit tougher, and the idea here is that you scale the size of the data set with the size of the number of processes, and you basically fully saturate everything. So yeah, that's what we did here. And yeah, moving on to the results. So this first slide, we can see a couple of things. So first thing to note is that there are two vertical axes, which is a little unusual, but I thought it was useful to kind of plot this. And so with the left axis, we can see that we're comparing the overall runtime, for each process count, and we can compare that to the data set size, which also scales up at each basically node count step. Interesting thing is that at 8, at a single node, the difference between DFuse and DFS, the native DFS interface, is negligible. But it starts to get more pronounced as more nodes are added, and also the DFuse runtime, or sorry, the DFS runtime stays pretty flat once you get past 16 processes. So I don't know, thought that was kind of interesting. Here we have, one other thing I meant to call out earlier. I ran out of time to do the checkpointing. So the results that I have to share today are for the read phase of training. I do plan to go back and redo the or add the checkpointing performance as well. So ping me if anybody's interested in that. But yeah, here we can see, the read throughput scales nicely with the number of processes and the data set size. And, we're getting, especially as we start to get into the larger process counts, we're basically doubling performance. And we're also scaling nicely with the data set size. And then on this slide, we've got, so my understanding of the samples per second measurement is basically kind of a proxy or a measurement of IOPS. And here again, we see that DFS outperforms DFuse fairly well. That's what I've got in terms of results. As I mentioned, I did do a previous benchmarking effort with a smaller data set and larger client counts. And we can see, this is from a couple of months ago, but we can see that, again, DFS, nicely outperforms DFuse and also is able to run at these larger client counts. That's the sample. So that's what I got. Happy to answer any questions.
All right. Thanks, Mac. Questions?
Should we consider the 8 and the 16 to be flat? It looks like it diminishes and then rises back up again. Is that an anomaly, or is that the way we should read it?
I was thinking about that. I got the 8, the single node results this morning just before this presentation, so I hadn't really had a chance to think about it too much. I think maybe it's the single node performance is better due to the lack of internode communication. It's all basically MPI on a single node. So maybe there's, I don't know. It is interesting though that the performance for DFS and DFuse are basically identical on a single node. You don't really see the benefit until you start scaling.
Yeah, and maybe I missed it because I was trying to do too many things at once, but what's the server configuration look like here?
So the servers, so again, this is, it's parallel store, so the actual details are kind of opaque, but so it's a 100 terabyte instance, so 25 servers with 1 engine per server.
Okay, so it's 25 ranks.
Yep.
And how many SSDs per engine?
There are 16 targets per engine.
Okay, got it. And then on the last ones, is it the same? The throughput numbers? Okay,
Yep.
cool, thanks.
Okay. One comment from myself. One of my colleagues has been using master to test the checkpoint functionality. It's been an improvement for our LLM code. So thank you for that, Google and Enacta.
Cool. Good to hear.